Okay, my fault. Well, ladies and gentlemen, it's a pleasure to announce the last but certainly not least lecture we are giving this evening. You all know when we are talking about cryptography and about cryptographic strength, we have this image of n,000 computers calculating for n,000 billion years and never getting to a result. Now, what good are these numbers? Today with us is David Hulton. He's been doing some research using FPGAs, free programmable grid arrays, and I hate this term, in effect bringing down the amount of time needed to break any, or to brute force any crypto system by many figures. And how he's done this and what effect this is going to have, he's going to tell us now. Faster owning assured. Thank you.
Thanks a lot. So, let's see here. Title of this talk is Faster Pwning Assured. A friend of mine came up with that. You can see that's FPGA, kind of. It's the new definition for FPGAs. And I'm going to be talking about basically how to use these things, how to harness, all the gates on them to do your will and just like crack stuff a lot faster than your PC. A little background about myself. I run a small conference in San Diego in California called TourCon, and so you guys should go to that. And I also do security R&D for a small company called Pico Computing, which is a company that manufactures these cards that I'm going to be showing you today. The card that I'm doing all these demos on is actually a little compact flash card. It's this big, and it's got a Vertex 4 LX25 on it, and I'll explain that a little bit more later. First of all, how many people here have done anything with FPGAs? Just a show of hands. Oh, great. Okay. How many people have cracked crypto stuff or done any crypto stuff on FPGAs? Anybody? Okay, great. Cool. So yeah, feel free to ask me any questions about anything or provide any feedback if I'm doing something stupid or whatever. And I run this little website called opencyphers.org that I post all my code on. All the code that I'm demonstrating today is all open source. You can download it and tweak it. It only runs on our hardware right now, but you can modify it and run it on whatever FPGA board you have. So a quick overview of what I'm going to do today. I'm going to give you a quick intro into FPGAs. It seems like a lot of you here know what they are, so I'll kind of skim over that pretty quickly. And then I'm going to go into some of the different crypto cracking stuff that I've done. I'm cracking WPA, but with modifications to cow patty. Cracking WEP, just brute forcing like 40-bit and 128-bit WEP. And I also have an implementation that cracks Landman that I actually presented on a couple years ago here at the CCC. So I'll just show you where that is today. And at the last minute, just about a week ago, I decided to work on Bluetooth pin cracking. And so I implemented a cracker that cracks Bluetooth pins if you actually capture the association. And I'm going to be demoing that with FPGA optimizations as well. And then there's a surprise release at the very end, so if you stick around, you might be able to see that. And then just follow up with some conclusions. So a quick intro into FPGAs. When you get a board like this and it has an FPGA on it, there's a lot of different things inside the FPGA. And it contains lots of general purpose logic like ANDs, ORs, XORs, flip-flop registers, block RAMs, all sorts of little components that you can connect together and have it basically function as any sort of circuit that you want. If you look inside of the chip inside of here, it actually looks like this thing on the right here, and that's a picture of the Vertex 4 LX25 die. You end up with some IOBs, which is these things along the sides and in the middle are where all of your pins, like underneath this chip, actually route into the FPGA. And so that's where all of your input comes in and your output goes out. And there's 448 of those on this particular chip. Then you have a bunch of general purpose slices, which are tiny little blocks with various different gates and things that you can connect together and configure how you like. And this one actually has close to 11,000 slices inside the FPGA there. Then there's digital clock managers that let you take clocks coming into the FPGA and multiply them up or divide them down or adjust the phase or basically manipulate clocks. And so kind of like on your old motherboards where you set a bunch of jumpers to set like, oh, I want this to run at 300 megahertz or multiply up, you know, my 50 megahertz clock to 400 or whatever. It's kind of the same sort of thing, but you can configure these. Then there's these block RAM little chips on there. There's 72 of them, and each one has about 18 kilobits of information that it can store. And it's kind of like a tiny little SRAM that you can just like store data in and pull data out of. So you can think of it kind of like the cache on your processor. It's extremely high speed, and it's on the FPGA, so you don't actually have to go out to other chips to pull in data or write data to them. So that's very useful. And then there's a row of DSP-48s, which are high-speed 18 by 18 multipliers and 48-bit adders. And you can configure these to do whatever sort of arithmetic you want. And there's 48 of those. And keep in mind that all these things can be doing things in parallel. So these DSP-48s can, in theory, get clocked up to about 500 megahertz. And you got 48 of them, so you can be doing 500 million times 48 18 by 18 multiplies per second if you use all of these. So that's quite a bit of speed compared to, you know, like modern day processor. And then there's a programmable routing matrix that lets you connect all these different devices together. So if you want to connect like a slice over here to like a slice down here, or connect it to like a block RAM over here, there's this whole matrix that lets you say, yeah, I want this to connect to that or whatever. So you can do pretty much whatever you want. Now, getting into WPA a little bit. This is how authentication works with WPA. And basically what I'm going to be doing is showing you that if you can capture all of the authentication handshake for WPA, you can go through and try different passphrases and figure out what the passphrase is for the network. And it's fairly simple. In this sort of diagram here, when you type in your security key or whatever your passphrase into Windows, that becomes your master key. And then it gets transformed into a pairwise master key using PBKDF2, which is kind of like a complex hashing algorithm. And then you get this PMK, which ends up being used for all of your encryption. And this PBKDF2 step is the most CPU-intensive step in the whole process. It actually ends up running about 16,000 SHA-1 HMAX, or I guess SHA-1s. But basically like about 4,000 SHA-1 HMAX. So it takes forever for it to do this one step, and so that's the step that I'm accelerating. To go in a little more depth onto how PBKDF2 works, you basically have, let's see here. You basically do a SHA-1 HMAC here using your passphrase and the SSID. The SSID is used kind of like the salt. And then you run through 4,000 times and do SHA-1 HMAX and just like take the output and stick it into the next SHA-1 HMAC. And so this step takes forever. And that just generates the first 20 bytes of your PMK. And so then you have to run this again to generate the next 12 bytes down here. So you actually have to do this twice, so it ends up requiring like 8192 SHA-1 HMAX in order to generate your PMK. Now, if you look at the SHA-1 HMAX, basically an HMAC is taking whatever algorithm, in this case SHA-1, and taking your first key and XORing it with 36 all the way across, and then also SHA-1ing like this T value, which is whatever you're HMACing. And then over here, you basically SHA-1 the master key XORed with 5C, and then SHA-1 the result of this. So essentially, you're kind of, for this initial one right here, you're doing a SHA-1 update with this value, and then a SHA-1 update with whatever your SHA-1 HMACing, and then doing a finalize and taking that and plugging it into down here. And why I show you this is because these two values right here can actually be cached because they're going to be the same result every single time, so you don't actually have to do those SHA-1s every time. You can cache the output of those, and then the only SHA-1s you have to do is this one and that one. So it requires a lot less work when you're doing SHA-1 HMAC, especially many times in this case. So after you run through this whole step, then you can basically compare it with all the network traffic you have to see if it's the right passphrase or not. My particular FPGA implementation uses 8 different SHA-1 cores, and it uses block RAM to buffer all the values. And I'll show you kind of how this works in a minute. But it uses kind of a ring buffer, so as long as you can keep the buffer full, it'll actually fully utilize all the SHA-1s. And this is somewhat how it works. I got this huge ring buffer, and it just starts filling up the top of it, all the way down to the bottom. So now all of these have values that it wants it to run the SHA-1 HMAC, or the PBKDF2 on. And then once it gets down here, then you initiate the whole thing, and it starts taking like the first 8 up here, feeds them over to the SHA-1s, those generate the values and sticks them back in here. And then it goes on to the next 8. And while it's working on these, then it fills up the other end of the buffer. So as long as you're filling these up, if there's any hiccups, then it still has all these full, so it can go through those smoothly and keep the pipeline full and stuff. So that's basically how that works. The result of the FPGA optimizations is if you run CowPatty on a normal PC, you get about like maybe 25 to 70 per second, depending on how fast your machine is. Using AirCrack, they have some MMX optimizations that run at like 100 per second roughly. With this little compact flash card, you get about 430 per second. So that's maybe like 6 times faster or so than a fast PC. And we also sell these in clusters, so if you have 15 of them, you can get like 6,500 per second and so on. Another cool thing is that we decided that we should generate some hash tables because lots of people use the SSID of Linksys or default or whatever, and so a lot of people are going to have the same salt. So why don't we just generate, a huge dictionary for those individual SSIDs? And so once we run across those, all the work is done, and we just run through all of our pre-generated values, and then we can crack it a lot faster. So this guy that I know, RenderMan, sent me this word list that has 1 million different commonly used passphrases in it, and also the top 1,000 SSIDs. And so he wanted me to generate all these pre-computed values. And this is kind of funny. The word list that he had was actually acquired through Google hacking and stuff he got from like Kevin Mitnick and some interesting sort of sources. So he tried doing this himself, and it took him 1 month to compute all this stuff on his lab of workstations, his cluster. And after computing for a month, he found out that his word list had return characters at the end of every line. It was in like MS-DOS format. And so most people don't have return characters at the end of their passphrases, so it was all work for nothing. So I did it on one of our clusters with 15 cards, and it took 2 days, so 15 times faster than his cluster. And these tables are actually, they're getting posted right now. I'm not sure if they're up on the internet yet, but there's going to be torrents out for them if you want to grab them. And then you can use CowPatty and crack people's access points if they're in the SSID list. So I'll give you a quick demo of this just so you can kind of see how CowPatty works. So CowPatty, there's all the source and stuff. I guess you can kind of see that. But this CowPatty application lets you just, if you have a capture, a dump of the authentication, then you can feed it this info, and it'll go ahead and crack all the stuff for you. There's also this GenPMK application that generates the pre-MK dictionaries. So you can use that. I generated some shell scripts here to make this a little bit faster. I'm going to start up CowPatty without the FPGA. And so here's a dictionary file, there's a dump, and there's a SSID, which is something clever. So I fired up a screen session. Right now, it's done like 100, 200, 300 passphrases there, so you can kind of get an idea. Right now, this is maybe running at about 50 per second, and